we have started discussing about media access control protocol. So, that is the data link layer main functionality we should say, and it is generally used in the access portion of the network. What we have done so far, we have discussed about a very basic protocol which is the Aloha, and we have seen that already kind of maximum 18% throughput can be achieved by Aloha protocol, which is a very basic random access protocol where all the users just whenever they have packet they transmit. We have done some analysis with some approximation. Okay. So, we have done that, and with that we have seen that maximum throughput what we can achieve. In the due course of this discussion, we will try to see how this intuitive understanding of the analysis actually gives us a better understanding of protocol and better proposal of a protocol. So, this is something which will be over the course of next few lectures we will try to appreciate that exactly how in the developmental phase a protocol has been developed through the extensive use of this Markovian analysis that we have already taken into account and we have learned that. So, we will try to see how that has been applied in the history of development of media access control protocol. So, that is something which we will be trying to appreciate. And in the meanwhile, we will also try to see how in the approximation how in a particular analysis the approximations are taken and how they are being relaxed and what is the consequence of them. Okay. So, this is something we will try to understand. So, in our journey, let us try to go to the next step, which is the slotted Aloha. Let us see how a very simple intuition gives us a better understanding of a protocol. Okay. So, let us try to see when we have talked about Aloha, what were our approximation, because we have also talked about any analysis, then approximation is very important. So, what is the system model for Aloha? It was like this. You have a common AR media where all the stations they have wireless interface and the system is something like this, or the understanding is something like this. They are getting packets. The first approximation was the Poisson arrival. So, that was the first assumption, that everybody is getting data independently with Poisson arrival. So, that is what they are getting. The second assumption was that the packet size was fixed. So, that was another assumption, that everybody was having some something to transmit, that packet size is always constant of size d, okay, both in time and in terms of number of bytes they have. So, in time also it is fixed because they have similar transmission rate. Okay. So, they are their interface is at the same frequency with the same modulation scheme and all those things. So, basically they have similar interface. So, that is happening, and what they do, they randomly access the channel. Okay. Randomly means completely randomly, in a complete distributed fashion. So, whenever he has packet, he immediately launch that packet. So, in time frame if you see, so this is user 1. So, whenever he gets the packet, immediately he puts it of duration d. So, this is user 1, that should be like this. If user 2 is there, whenever he gets packet, he will immediately put it of duration d. Now, if they have common region, because it is a common media, so the packet will collide and you do not get anything, both the transmission will be erroneous. So, this is what we have assumed, that whenever they have packet, they will immediately transmit. What are the other assumptions that we had? So, the other assumption was regarding what happens to the packet once he transmits. So, if he transmits the packet, now we have to see what happens, what are the possibility. Whenever he transmits, there are few possibility, or if he does not transmit, so there are few possibility. The one possibility is that the packet will be successfully received at the other end. So, if he is trying to transmit it over here, the packet will be successfully received. That will only happen if no other transmission is coming within this period of his transmission. If that happens, then the packet goes successfully. If there is a collision, the packet will not be received successfully. So, whether it is a successful transmission or unsuccessful transmission, this feedback the station must get. So, that is the feedback. So, we call it 0, 1 E channel feedback, and this is immediate. So, 0 means no packet transmission, 1 means successful packet transmission, E means multiple stations are transmitting packets simultaneously. So, there is a collision. Okay. The fourth assumption was that due to channel there was no error. Okay. When I transmit the packet and if it is successful, then there will be no other errors. Okay. So, let us errorless either that or the error has been already taken care by the source coding. Okay. So, this has been done. So, this is our next assumption, and the feedback must be immediate. What does that mean? That means whenever this transmission is done, immediately by some mechanism the station who is transmitting, he will get the feedback. We will later on see how this immediate feedback can be accounted for because either the feedback can be that he actually transmit an acknowledgement, this is something we will appreciate later on, or by some other mechanism from the physical channel only you can get feedback, that also we will try to appreciate. So, how this feedback is, this immediate feedback is given to the user, this is something we will try to see how physically we can make that. So, that is another thing. So, these are the means basic 4 assumption. What are the other assumption? The other assumption is that when there is an unsuccessful transmission, what do I do? So, then I do retransmission. So, basically it is like this, he has a buffer, whenever the packet arrives he immediately transmits it and keeps that in the buffer. Okay. Remember that buffer has only size 1, which will come in the next assumption. So, it keeps the packet over there in the buffer, and whenever he sees that the channel is free, he immediately tries to, whenever he gets the packet, immediately he transmits the packet and keeps that in buffer. This is what he does. Okay. So, once he has done that, okay, so this is what he does, he keeps the packet. If the packet is successfully transmitted, then immediately he will be getting feedback by some means, whatever that immediate feedback we are talking about, he will get that feedback and then he will discard that packet and wait for the next packet to arrive. Okay. In between this process, if another packet arrives, our assumption is no other packet arrives. If it arrives, we discard that packet, okay, because the buffer size is maximum 1. He can only hold 1 packet. He will just hold it till the retransmission or till the transmission has been successful. If the feedback comes as unsuccessful, he will attempt retransmission. How he attempts retransmission? That is another part of the protocol, description of the protocol, that he probably randomly choose a later time to transmit it. We have said that it is again exponentially distributed time after which he tries to retransmit that packet. How much exponentially distributed, that is something we have not commented on. Okay. Somehow with some exponential distribution he tries to do this. Okay. How he does that, that is something we will try to understand slowly as we go inside the protocol. So, this is what will be happening, and then the last assumption 6 is what we are talking about, that either it is bufferless, that means he has only one buffer, he cannot store multiple packets. The assumption is either his rate at which he is getting packets is so slow that he can only think about one packet, after a long duration the other packet will come, by that time there will be some successful transmission. So, either it is like this, or we can also assume that if in between some other packet comes, that will be discarded. Or the other version of this approximation is there are infinite source. Together all source gives a packet transmission rate of lambda. That means individual has infinitesimally small rate. So, therefore, they will never get next packet, okay, because their rate is infinitesimally small. Okay. So, inter-arrival is almost infinity. So, therefore, each of the station will never get the next packet. So, it is like this, every packet comes from a new node. Okay. So, as you can see, these are all restrictive approximation, and with that approximation we have done some analysis. Okay. Only thing that we have still not characterized is this retransmission. This is something which will be characterized now, later on, we will see that, okay, slowly, because initially our assumption was, okay, it's some adjustable Poisson rate when I am doing retransmission. If this is unsuccessful, after this with some exponential distribution time, he will be again reattempting. So, this is that reattempt thing that we are talking about. What that will be, we have still not characterized. What should be the parameter of that? So, if this is mu, what should be that particular mu? We have not characterized it. Okay, we'll try to see that. As I said, somehow this will be done, and then overall arrival rate we have talked about is some Gn, okay, or G. Let's forget about this. Overall arrival rate will be G, which is greater than this lambda, because there are some more arrival which are happening due to this unsuccessful transmission when you are trying to attempting retransmission. They are also independently, because the inter-arrival is exponential. So, they are also Poisson, they will be merged to this Poisson, and overall things will be some G. So, with lambda some more things will be merged, they are all independent Poisson. So, overall things will be still Poisson with arrival rate G, and with that we have done some analysis, we have seen the characteristics, something like this, okay, and we have seen that it reaches up to 1 by 2 E, okay, which is basically the 18% that we were talking about, okay, approximately 18%, okay, and it reaches at half, and so when G equals to half, okay. This particular graph also we will try to describe it in a more generic fashion when we go to slotted Aloha, then we will understand it properly, okay. So far we have done this. Now, on this we will now add one particular description, which is called the time is slotted. So, let us say 1 A we do, and we say the time is slotted. That is when slotted Aloha comes into picture. We want to see this. So, where from this has come? Let us try to analyze that. It is embedded in the analysis itself. So, in Aloha what was happening? Suppose I want to transmit a packet. What is the overall vulnerable time when this packet might be collided? Because that is what I am interested in. So, if he gets the packet at t, we have seen that up to t plus d, so this time t plus d, any other station gets a packet, it is vulnerable, that means there will be collision. Not only that, beforehand also, if I consider up to time t minus d, within this also if somebody had arrival and that was already being transmitted, that also will be vulnerable, because there will be common zone, common region of time where they will be simultaneously transmitting in the channel, and this will be creating collision. So, overall if you see t minus d to t plus d, that is the vulnerable period, that is 2d amount of vulnerable period is there, where I have to make sure that no arrival is happening. If I just make time slotted and just do a little bit modification of this, we say it is like this. If I have a time frame, this time frame is slotted, every slot distance is d, which is the exact time of a packet transmission, okay. So, every slots are of duration d, I do the time slotted, and the additional thing that I will have to do, which makes the system more complicated, that everybody has to have this synchronous essence of time. So, that means they know exactly when this time slots are started and when they are ending. There is a global synchronization, and this synchronization is somehow being maintained among all these distributed node, user 1, user 2, user 3. So, if it is user 1, user 2, user 3, so it is distributed among all these nodes, and they all know about this synchronous timing. This is something which is approximated. Their transmission now, I put a restriction. What is happening now? I say earlier whenever they were having arrival, I was immediately transmitting. Over here he was getting an arrival over here, immediately he was transmitting, right? He was putting the transmission. So, whenever there is an arrival, he was immediately transmitting. Now, what we want to do is, we do not want to do that, we will restrict it. So, the arrival might happen over here, but the restriction is because they have a synchronous time essence, they will only transmit over here, the slot boundary. So, previous slot, whoever has received packet, they will attempt immediately in the next slot boundary. This is exactly what we do. Okay. So, every arrival will not be immediately transmitted, they will wait for that slot to be completed and immediate next slot they will immediately transmit. Again, they do not consider about what others are doing, they will do their things. So, if suppose user 1 gets a arrival over here and user 2 gets another arrival over here, both the user will start transmitting over here, user 1 transmission over here and user 2 transmission also over here, and then there will be collision, of course. Okay. So, now what is happening? Within a slot duration d, if there are multiple arrival, then there is a collision. Can you see the vulnerability period has been reduced just by doing this? Because earlier within 2d, any arrival was creating collision. Okay. So, if one transmission is going on within 2d, anybody makes arrival, I will have a collision. Now, over here what has happened? Only within d, if more than one is arriving, then there is a collision. If nobody arrives, then nothing happens, the slot remains idle, nobody transmit. So, if suppose within this slot nobody arrives, then next slot remains idle. So, that is why this 0 1 E is happening. So, 0 means no arrival in the previous slot, 1 means one arrival in the previous slot, E means multiple arrivals in the previous slot. Okay. I am talking about arrival, there are something more also, because now there is retransmission also. So, now let us try to see with this particular scenario what happens to my retransmission. So, let us try to understand. So, let us say there are m number of stations. Okay. So, m number of stations are there. So, I am now taking a finite station approximation, not infinite source. This infinite source I am not taking, we will come back to that later. So, finite number of station with bufferless approximation, that means they have only single buffer, just for retransmission the packet will be remaining over there till he gets successful transmission. Once he gets successful transmission, he will discard that and then wait for the next arrival. In between, if any arrival happens, he will discard this. Okay. So, this is the approximation we are taking. So, there are m station. Okay. Out of this m station, what might happen? I can segregate them into two class of stations. One is called the backlogged, and these are fresh. So, what do I mean by this fresh and backlog? Backlogged means he has already attempted a transmission, it's kind of memory. He has attempted a transmission, but his last transmission was unsuccessful. That means, when he was transmitting, multiple other nodes were also transmitting. So, because of that, there was a collision and his transmission was not successful. So, that is why he is now waiting with his packet in buffer to get a chance of retransmission. Okay. So, earlier we have given a vague, when we were trying to describe the scenario for Aloha, we have given a very vague description of when he will be transmitting the packet, that some exponential distributed time after. Now, over here we will quantize that. Now, the time is slotted, okay, I can quantize. So, what I can say that next slot he will attempt, but with some probability, let us call that as QR is his attempt probability. That if he has been unsuccessful, because he gets immediate feedback. So, suppose 2 has arrived over here, user 1 and user 2. So, let us take this scenario, user 1, user 2 has arrived over here, only 2 users are there. So, m equal to 2, we have only user 1 and user 2. Earlier user 1, user 2 does not have any data, both their data arrives in this particular time. Okay. So, let us say this is time frame k, this is k plus 1. This is k plus 2 and so on. At k, 2 arrival happens. Immediately next slot, both of them will be attempting, so they collide. So, the feedback goes to both as E. How this will come? We will not think about that. will assume that immediately after the transmission he gets immediate feedback and no more time is required, and somehow he has some resources to get that feedback. So, he gets this feedback that transmission has been collided for both the users. Now, both these users will be backlogged. So, now this out of m, if we say that n number of users are backlogged and m minus n number of users are fresh users who can take new arrival. So, what has happened earlier at this point, how many users were fresh? 2. How many users were backlogged? That was 0. At this instance, still same thing. Okay. So, basically 2 users had made arrivals, but still they have not transmitted, so they are still not backlogged. So, 2 users are fresh, 0 users are backlogged. Over here collision happens, immediately they will know that okay, these 2 users are backlogged. So, immediately at this instant the state will be changed. So, he has 0 fresh users, both the users are backlogged. Now, for the backlogged user, what we are saying, this is the protocol, that they will be transmitting immediately in the next slot with a probability of QR. Okay. What will be the value of the QR? That will decide later on. So, that will be our part of the analysis. But this is what we are saying, that immediately in the next slot they will be transmitting with probably some probability QR, nothing else. Okay. So, what does that means? Is that memoryless now? That when he is transmitting, let us try to understand this particular part. So, next slot he will be transmitting with probability QR. What about the next slot? Again with probability QR. So, what's that is constructing? What is the probability that he will be finally transmitting at the next k plus ith slot? That you immediately know that in between all these I minus 1 he does not transmit. So, that means 1 minus QR is the probability that he will not transmit to the power I minus 1, and then ith slot he will be transmitting QR to the power I. That is the probability that he will be attempting at the ith k plus ith slot. This is a known distribution, we already know this. This is a geometric distribution, which is again a memoryless distribution. Because the time is slotted, now everything will be discrete. So, this distribution also becomes the discrete version of our exponential distribution, which is geometric distribution. So, as we can see, almost the things remains the same. Okay, whatever we have decided earlier, almost similar things remains over here. Our description remains over here, where we are talking about a particular geometric distribution now, okay, for every station. So, they will attempt this. What will now happen if both of them collide? Why we are putting this probability value? That also there is a reason for that. Let us try to think, if 2 nodes goes into backlog, it might be 2, it might be more than 2, okay. Whoever goes into backlog, in the next slot, immediate next slot, if both of them attempt, they will again collide, and this will never be resolved because they will keep on colliding in every slot. So, the entire time slot will be all collision and nobody will be able to resolve the collision. So, by putting this probability, we are actually randomizing who will be transmitting. If more than one station has transmitted, that means I have to now resolve the collision, otherwise I will not be able to actually give chance for transmission to one. So, this collision resolution is coming up with the very basic idea of putting this probability QR, as you can see. This also gives you a very basic idea in Aloha, what we have told, that take a random randomly driven exponentially distributed amount of time after which you will be attempting. So, immediately next you do not attempt. Over here we are giving a chance to do this transmission immediately next, but that is with a probability, again that makes these things random. So, basically whenever there is a collision, we are somehow resolving this collision by randomizing these things. That means putting a probability of QR into this. So, now as you can see that what will be the possibility of transmission over here? That is now a mixture, because some of the nodes might be backlogged. So, it might come from them, their attempt, or some new arrival can also happen if there are some fresh node. So, it is a combination of these two which will be attempting a transmission, and then from there you have to understand whether there is a collision happening or not. I hope that makes the whole system very clear, crystal clear. So, this extra things we add to this whole description of Aloha. So, I had a earlier very simple method. Now, we are putting some extra description to it, and with this extra description, the first description we are given, we have slotted it. We have also observed why we have slotted the time, because the vulnerability period we could reduce. That was the intuition which was coming into our mind while implementing this. So, we could reduce that vulnerability period, and after doing that reduction with respect to this distributed feedback and retransmission mechanism, we have devised a particular mechanism. And why we are devising that mechanism? Again, we are putting this probabilistic retransmission because we want to resolve the collision. So, this is the first method probably towards resolving collision. So, once we are in collision state, we need to resolve the collision. It is always true. Suppose I can give you a very simple example. Suppose you have a narrow doorway, and then two fellows are trying to attempt. If you keep on attempting, nobody will go through this. What we do? We make an understanding among ourselves. So, whenever there is one of the guys says, okay, you go first, because if you go, then the door will be clear and then I can get the chance. That same thing is happening over here. Two nodes who has been collided, they are in a distributed fashion, they are trying to resolve this collision. So, that conflict which was happening at the entrance of a doorway, same thing is happening over here between two stations who doesn't know each other. Okay. So, they are trying to resolve it. How they can resolve? By randomizing this. So, this probabilistic attempt is the main architect behind resolving collision. You will see that later on. We will try to describe this in a more detailed fashion later on, but this is the basic idea behind it. Okay. So, after all this description, can we now analyze this? Let us try to see that. So, is there a possibility that will be able to analyze this? So, for analyzing, let us try to see how do I analyze this. It is all random, exponential arrivals are happening, you have this attempt also is some probabilistic thing. So, it is a random process, of course. This random process has to be analyzed. Can we see that it is a Markovian process? Why it is a Markovian process? Because the retransmission, all the events, arrival, that is Poisson. Okay. So, arrival is Poisson, time is slotted, of course, and this particular retransmission attempt, that is also we have given this probabilistic description, and once we have given probabilistic description, it has become again geometric, which is again memoryless. So, everything, all events are memoryless. So, therefore, it has a potential to become Markovian, and the time is slotted. Only things which are happening is at the boundary. Of course, arrivals are happening over here, but with arrival what I am doing, that is at the boundary. So, basically from the system perspective, it is still at the slot boundaries only. So, discrete times events are happening. Therefore, I can say it is a clear candidate of DTMC. Once I have this understanding that this will be analyzed by DTMC, now can I go one step forward to see how do I describe the state. So, now I have to describe the state in such a manner that that state summarizes everything. I do not need anything else. So, let us try to see, is there something which summarizes everything? The thing that summarizes everything, carefully think about that, is the amount of station which has gone into backlogged. This n. Okay, there are m stations, among them n station has gone into backlog. So, always what will be happening, after every attempt there will be this backlog station which will be modified, and that is summarizing everything. You do not need any other description, because what will be happening, if multiple fellows attempt, then they will all go into backlog. So, backlog will be increased, number of stations which are backlogged will be increased. If nobody attempts, means nobody comes over there and no retransmission attempts is being done, then it will go in idle. So, backlog remains the same. If some new suppose there are a successful transmission, then what will happen? One of the backlog stations might have a successful transmission, then he will be actually relieved from this backlog to fresh, or he will come from backlog to fresh, the overall backlog station will be reduced. If a new station attempts and no other backlog stations or no other new station attempts, he will be successfully transmitting, again the backlog station will remain the same. So, this only number of, if you keep track of number of backlog stations, that describes the whole state very nicely. You do not need any other description, because this description when this has arrived, that is not required, because it is all about Poisson arrival, it is exponential. So, I can take that memory out, I can think that all these through has freshly arrived over this boundary. That we can do, we have already seen that. And how much time he is in backlog, that is again geometric, so it is memoryless. So, every slot I can forget about that memory, how much time he has a station, if he is in backlog, how much time he is in backlog, I do not have to consider that, because that is again a geometric distribution. So, it is a memoryless process. So, therefore, just taking the number of station in backlog describes my state. Okay. So, it can start from 0, goes to 1, 2, up to m. At max m number of station, all stations might be in backlog. That is the whole thing. That is my state description. Now, I need to populate the transition matrix, the P matrix. This is where now I have to see from the system description, can I get the description of this transition matrix. Okay. So, for the transition matrix, one probability I have got for the backlog station. If he is in some backlog station, means backlog state n, from there each of the station with probability QR will be attempting transmission in the next slot. Okay. So, in the next slot what will be happening, that probability I have to get, because probability transition matrix is this, that at time k it is in some state, let us say it will be 0, 1, 2, whichever state he is assuming, from there at time k plus 1 where he will be going. So, that transition matrix I want to calculate where he will be going and what is the associated probability. This is what we want to calculate, right. So, if we wish to calculate that, we will have to now see how do I get this probability calculation. So, one probability value we have got already, QR. Now, for the fresh station or the station which has not been in backlog, for them how do I calculate what is his transmission capability or transmission attempt. Overall arrival rate is lambda. This is actually a Poisson merged function of m stations. So, basically m station, there are total m station which makes arrival Poisson arrival, and they are all identical station, they makes Poisson arrival, and with that overall arrival actually I get a composite Poisson arrival of lambda. Okay. So, if that is the case, then each individual how much arrival strength they will be having? They will be having lambda by m, because they are all symmetric and they are all homogeneous. So, each individual station will be attempting a Poisson arrival of rate lambda by m, right. Now, within a slot duration, okay, let us call it d, and we take d as unit, d as 1. So, within a slot duration of 1 or d, whatever it is, what is the probability that one particular station will be attempting a transmission? Okay. So, how do I calculate that? So, that attempt we are characterized by lambda a. So, this is something we want to characterize, that the value of this lambda a, okay, that a particular station will be attempting transmission. How can I calculate that? First, let us try to see what is the probability that he will not have an arrival in this d or in this unit time. So, that is e to the power minus lambda by m, that is his strength, into d, or if d is 1, that will be 1. So, if d is 1, d is equal to 1, it will be e to the power minus lambda by m. So, this is the probability that he will not be attempting any transmission, or he will not be having any transmission within this d. What is the probability that he will be having this lambda a? That must be 1 minus this, 1 minus e to the power minus lambda by m. So, we have got this two probability, one is this and one is this one, okay, QR. So, these two probability we have got. Now, in the next class what we will try to do, taking these two probabilities, we will try to see how do I calculate or how do I populate this P matrix of this particular Markov chain. Okay. This will give you one essence or one example of how to develop a DTMC and then how to analyze that. Okay. Thank you.